Srivastava from University of Wisconsin. She's a graduate student there working with Andreas Seeger. And she will talk about Lebesgue space estimates for spherical maximal functions on the Heisenberg groups. So, Rajula.
Thank you, Professor Tangavelu, for the introduction, and to you and all the organizers for inviting me here. I've come to IC before twice as a summer student, and I was always very intimidated, and it's still a bit intimidating, but it's an honor to speak here in the Hudson now. All right. So as I said, I will talk about Lebesgue space estimates for spherical maximal functions on Heisenberg groups, and this is based on joint work with Joris Roos and my advisor Andreas Seeger. So let's start. So I will start by first specifying all the notations. So we would be talking, our setting today would be the Heisenberg group Hn. So when I say n, you should think of it as of Euclidean dimension d equals 2n plus 1. So 2n being the horizontal plane and 1 being the vertical perpendicular direction. And I will write each element x of the Heisenberg group as I'll also break it in the same manner. So the first x under bar would mean the first 2n directions, and xt is the last vertical direction. And then in this notation, in exponential coordinates, I can express the group law for the Heisenberg group in this manner. So the product of these two elements, x and y, is given in this manner. So in the first 2n directions, you just add the coordinates up, x under bar plus y under bar. But in the last coordinate, you have xd plus yd, and you have this bilinear form, which is given by this J matrix. And this J matrix is just the standard symplectic matrix, which is given in this form. So here In denotes the identity matrix of order n. So this is what it is. And if you want to actually see how this looks like, so for example, when n equals 1, meaning the total dimension is 3, let's write the product out. So again, in the first two coordinates, you just have you just add the coordinates up. But in the last coordinate, you have x3 plus y3 plus now this Heisenberg twist, x1 y2 minus x2 y1. And as is obvious that this is non-commutative, if you swap the roles of x and y, this would become the negative of this. So this makes the product non-commutative. So this would be our notation. Right. Okay, so my title says that this is a spherical maximal function, and whenever we think of spheres, we always think of a hypersurface of codimension 1. However, for the purpose of this talk, whenever I say spheres, it will not mean a codimension 1 surface, it will mean a codimension 2 surface. So how you should visualize it is in this manner. So R2n is this horizontal plane. And then the last coordinate is this vertical direction. And then I'll be considering averages over these horizontal spheres in this plane. So basically S2n and R2n, which in the horizontal plane is of codimension 1. However, in the overall Heisenberg group, it's of codimension 2. So it is a more singular object than the usual spheres. So I put spheres in quotes, but from now on, I would put spheres without quotes, and they would mean this codimension 2 surface. So let's see, averaging over codimension 2 spheres. So let's consider this horizontal sphere of codimension 2 in the Heisenberg group centered at the origin. And let's consider a normalized rotation invariant measure on it. And then we consider the average on the sphere. So ATF evaluated at x means it's basically the operator which returns the average of the function f on a sphere, on this codimension 2 sphere centered at x and of radius t. So this is what it's happening over here. But because of the nature of the product on the Heisenberg group, you have this in the first 2n coordinates. But again, in the last coordinate, this matrix J comes up. And then when I say maximal functions, so this is basically, I mean, the most obvious choice might be to look at the global maximal function, which is where what you do is you take the pointwise supremum of the action of AT on F for all radii t. So supremum over all t greater than 0. So this is the global maximal function, which I will always be denoting by frac m. However, our focus in this talk would be on the local maximal function, which I'll just be noting by m, where the supremum is taken only over radii at a single scale. So radii of t from 1 to 2. So these are the operators that we'll be looking at. So let me talk briefly about the history, and let's start with the Euclidean spherical maximal function because that's how the story started. So in 1976, Stein considered the Euclidean spherical maximal function, and he proved the result for RD for d greater than equal to 3. And he said that the global maximal operator in the Euclidean case is bounded on LP in the range p greater than d over d minus 1. And this is also an optimal range. He also has an example to show that this is optimal. So, however, this result was not proven for d equals to 2. In fact, for d equals to 2, this is actually 1, right? So you don't have L2 methods available. So it was more difficult, but 10 years later, Bourgain proved the d equals 2 case as well. And then later, this result was generalized in the variable coefficient setting for general Fourier integral operators by Mukenhop, Seeger, and Sog, using notions of cinematic curvature and a lot other things. And then this was followed by the work of Schlag at first using geometric means, and then Schlag and Sog using some analytic means, establishing almost sharp LP to LQ estimates for the local Euclidean spherical maximal operator now. And then some years later, Lie proved weak type estimates for the Euclidean maximal operator at some of the endpoints, but again for the local case. Right, so all this happened in like late 90s basically, but then the spherical maximal operators have come into prominence again, because more recently in 2017, Lacey used estimates on Lacey proved some sparse bounds on the global maximal operator in the Euclidean case. And he used these near optimal LP to LQ estimates for the local maximal operator as an essential ingredient to prove sparse bounds for the global Euclidean maximal operator. And using these sparse bounds on the global spherical maximal operator, he was able to prove some new weighted inequalities. So that's why they've become interesting again. But this is the Euclidean story. Let's come to the Heisenberg spherical maximal function, which is the object I just described. So I think there's a bit of a lag, maybe. Right, okay. So this object was introduced by Nevo and Thangavelu in 1997. And then the global maximal function was considered first, and a sharp result for LP bounds for the global maximal function, analogous to Stein's result, was proven in 2004. And the interesting part is that it was proven in two separate papers using completely different methods, but the same optimal result was proven. So the first paper was by Narayanan and Thangavelu, were the two speakers right before me in this seminar. And independently and by a different method by Muller and my advisor Andreas Seeger in 2004, and it also appeared in Israel Journal Math, both the papers, I think. Right? And what was the result? So like Stein's result was for d greater than equal to 3, this result is for n greater than equal to 2. And for n greater than equal to 2, the LP boundedness of the maximal function holds if and only if p is greater than 2n over 2n minus 1. So it's again an optimal result. And here, let me make two remarks. The first is that in all the results that you will see here, I'll have this condition n is greater than equal to 2. For n equal to 1, for the Heisenberg group H1, this problem is still open. Even the LP bounds for the global maximal operator is still open, and it's regarded to be quite hard in general, although more recently there were some partial results in there, or in special cases. The other remark I want to make is that, so in the talk today, I would not be talking about the techniques used in this paper and papers of this type, and all the experts here about that. I would be focusing more on the kind of approach used by Muller and Seeger in their paper. And this was the approach of using Fourier integral operators in the context of the Heisenberg group. And that's, it's a bit surprising or amazing that you can actually use this theory, which was developed in the Euclidean setting, but you can stretch it so far as to also consider the Heisenberg setting, which is very non-Euclidean. However, it does have a lot of structure. So this is what we would be seeing today: how to use this theory, existing classical theory for integral operators, in this setting. All right. Now let's come to more recent results and what we'll be focusing on today. So let's talk about the LP-LQ estimates for the local spherical maximal function. So very recently in 2020, Bakshi, Het, Ronkal, and Tangavelu considered sparse domination results for the global spherical operator M with consequences for weighted inequalities. So just like Lacey did for the Euclidean case. And in line with Lacey's approach, as an essential ingredient, they had to establish LP to LQ estimates for the local maximal function M. And this was their theorem in 2020. So they showed that M maps LP to LQ for n greater than or equal to 2 on the Heisenberg group, whenever 1 over P, 1 over Q belongs to this region, which is a triangle with corners 0, 0. So this second point, these 2 points are on the diagonal, 2n minus 1 over 2n, 2n minus 1 over 2n. So this is basically the also the LP result. And then there was this third new point on the anti-diagonal, 3n plus 1 over 3n plus 7 and 6 over 3n plus 7. Another question was if this result is sharp. And so this was our focus when we consider this problem, to look for a sharp result, a sharp LP to LQ result for the local maximal function on the Heisenberg group. And in our result in 2021, we were able to prove it. So this is again Joris, Roos, Andreas, Seeger, and myself. So for n greater than, again, let n greater than or equal to 2. And now for us, the region we come up with is a quadrilateral. So Q1 is and Q2 are the same as the previous result, but Q3, the point on the anti-diagonal, goes a bit further. So this is n over n plus 1, 1 over n plus 1. And the point Q4 is a bit of a weird point. It's not on the diagonal, it's not on the anti-diagonal, it's on this other line which passes through the origin. And we'll look more into it as we go further in the talk. And our result is also almost sharp in the case that we prove that M maps LP to LQ. M from LP to LQ is bounded if 1 over P, 1 over Q belongs to the interior of this region, of this quadrilateral. Also, if 1 over P, 1 over Q belongs to the exterior of the quadrilateral, then we show that M is not bounded from LP to LQ. So it's almost sharp up to the endpoints, the edges. If you look at a result in a paper, we also have some partial results on some open boundary segments on the edges, and a negative result for Q2 and such. I mean, although we have not covered everything, and these are weak type results, but in this talk, I will not be getting into those technicalities. Just let's look at this almost sharp result. So this is the main theorem. So these are the coordinates, but it's always nice to have a picture. So this is the region R that I'm talking about in our theorem. So you have a point Q1, Q2 on the diagonal, then this is Q3 on the anti-diagonal, and Q4 on some other line passing through the origin. So this is our the region that we get. Okay, so now for the remainder of the talk, what my plan is that in the first 15 to 20, in the coming 15 to 20 minutes, I actually would like to talk more about how we actually get the conjecture of the theorem. How do we get these coordinates? And the way we get them is, in other words, how do we prove the sharpness of our result? We do this by actually coming up with counterexamples corresponding to each of the edges, which show that you can't go beyond them. So that would be my plan. So I would like to talk about those counterexamples first. And then in the time remaining, I would talk about the ideas for the positive result of the theorem. So first of all, look at Q1, Q2 is just saying the condition is that Q should be greater than or equal to P, which is a standard condition when we are looking at LP to LQ improving results. So that's fine. In particular, I'd be talking about the example for Q2, Q3, Q1, Q4, and Q3, Q4. Now, if you have looked at the figure corresponding to the Euclidean local spherical maximal function in this Schlagstock paper, this picture might remind you of their picture, but there are some differences. First of all, for them, Q2, Q3, the edge Q2, Q3 is parallel to the 1 over Q axis. It's perpendicular. And the reason why we don't have it to be perpendicular is because it has something to do with the fact that our codimension is not 1. The numbers come out to be that way. Also, the point Q4 for us occurs in a different way than in the Euclidean case. So in the Euclidean case, the counterexample corresponding to the edge Q3, Q4 is actually a standard nap example. And in our case, we come up with a new counterexample for the Heisenberg group. You can try to generalize the nap example to the Heisenberg group and you get the condition, but it turns out to be not sharp. And we were able to come up with a new counterexample, which actually gives you the sharp condition and you can match your positive result. And as far as we know, this counterexample, even for Heisenberg group, has not appeared before. So this example is new for us, and that is why Q4 occurs in a different way for the Heisenberg group than the Euclidean case. But the examples for Q2, Q3, and Q1, Q4 turn out to be straightforward generalizations of the Euclidean setting. So that's what it is. So let me first talk about these Q1, Q4, and Q2, Q3 counterexamples, which also will turn out to be duals to each other, and then the interesting Q3, Q4 example. So the counterexample for the edge Q2, Q3, you should have this picture in mind. So if I want to get a condition for my maximal operator, what I need to do is I need to come up with a test function, and then I need to test my operator on the test function on certain points, on points lying in certain sets where the output would be large, and that would give me the best condition possible. So this is what I'm going to do now. So right. So here, what would be my test function for Q2, Q3? So my test function, I'll call it F delta. And this is just the characteristic function of the ball B delta, which is basically an actual ball and it's of radius delta, kept at the origin. So this is the ball, the blue ball that I've kept over here is what you should be looking at. So this is of radius delta. So this is my test function F delta. And now let's first consider a single radius, single averaging operator, and then we will look at the maximal function. So let's look at the average for a sphere of radius 1. So F delta. So I'm taking an average of F delta on a sphere centered at X, and this sphere is of radius 1. And now my question is, for which points would this average be large? Now, geometrically speaking, since F delta is the characteristic function of this ball, this blue ball over here, basically what I'm asking is, what are the points for which when I take the average, the average, a substantial part of that average would actually hit the sphere? And that, I mean, when you think about it this way, then it has to be this annulus that I have, the red annulus over here. We call it R delta because when I take I take a point X over here and I try to take an average of radius 1, it will definitely hit my sphere like this. Right? So this is so basically A1 F delta X, absolute value of this, would be greater than or equal to what? So how much of the portion is captured in this ball? So a cap with radius proportional to basically with radius about delta. So the area which is caught over here is something like delta to the power 2n minus 1 because it's a 2n minus 1 dimensional object. So this A1 F delta X would be greater than or equal to delta to the power 2n minus 1 for X in this annulus. So let me call this annulus R delta 1 because it's near the point 1 for X in R delta 1. Right. Okay, but it's not enough to just consider the single annulus because remember, we are not taking just a single average. We are actually taking the supremum over all averages from 1 to 2, meaning there are a lot more radii possible. So that means I will actually have to take concentric rings of these annuli. So there's so for example, this annulus I would might correspond to a radius say 1.5 or something, and it will again hit this thing. Okay? And these annuli, let me say, are of thickness delta in 2 directions. So it's of thickness delta in this direction, and also delta in the vertical direction. Okay? So to sum up, what is happening here is that the region, the test, the the sets on which in my test points lie, these x's, is going to be something like r delta, which is the union of individual analyte like this. So r delta t, where these points t are delta separated, because I will be taking analyte of thickness delta, r delta 1. And what's the volume of r delta then? So the volume of r delta is just, so first of all, since I'll be taking, how many analyte would I be considering? So I'm filling the entire interval from 1 to 2 with analyte of thickness delta. So it will be delta inverse number of analyte. Delta is a small number, so delta inverse is something large, times the volume of each of these analyte. And these analyte only have thickness delta, they are of order 1 in every other direction, but in one direction, horizontal direction, and one vertical direction, they have thickness delta. So the volume is delta square. So this would just be delta, right? Okay. So then basically, when I test my inequality, so what I'm saying is that mf delta x would be greater than equal to delta to the power 2n minus 1, this delta to the power 2n minus 1, on this r delta. Okay, so now when I test my inequality, this is mf delta lq, this is what I want, right? Less than equal to f delta lp. So I have already calculated what so what is f delta? F delta is just a characteristic function of this ball, which is a volume delta to the power 2n plus 1. So this LP norm of this will just be delta to the power 2n plus 1 over p. And we've already established that this mf delta is greater than equal to delta to the power 2n minus 1 on r delta, which is of volume delta. So you have delta to the power 1 over q. So then the inequality I get is delta to the power 2n minus 1 plus 1 over q is, let me see, yeah, less than equal to delta to the power 2n plus 1 over p. And as I said, think of delta as small. And as we take delta going to 0, the condition we get is 2n minus 1 plus 1 over q is greater than equal to 2n plus 1 over p. And that's exactly the equation of the edge q2, q3. And I'm just saying that this is basically the example in the Euclidean case. You just take delta thickness in the vertical direction. That's it. So this is basically the idea. And let me quickly show the counterexample for the edge q1, q4. And as I said, it's dual to the previous one. So think of the same picture. In fact, it's slightly easier because now you only have to consider a single average, and which already gives you the sharpness. But it's dual, meaning now you flip the roles of the analyst and the ball. So now your characteristic function f delta is the characteristic function of this analyst of thickness delta in two directions. And your test point, the points you would test your average on. So f delta is the characteristic function of the analyst, and then you test, or you look at A1. So just consider the average of radius 1, f delta x, for x lying in this ball now, b delta. So then you can do the same thing, and you would, but okay. So now when when I'm taking the averages, I'm taking averages centered at points lying in this ball. And when I take the average of radius 1, this time the analyst catches almost the entire sphere. So for x in b delta, a1 f delta x, this would actually be bounded below by a constant. It almost catches the entire radius. So then again we build the same inequality. So in fact we can just look at a single radius this time. So LQ, or basically what we are going to get is something like this. Again, so this time this is the volume of the test points. So I'll have something like b delta to the power 1 over q times 1 is less than equal to the volume of the analyst. So delta to the power 2 over p. And the volume of the ball is just delta to the power 2n plus 1. So I'll have delta to the power 2n plus 1 over q is less than equal to delta to the power 2 over p. And as we take delta to 0, this is just 2n plus 1 over q is greater than equal to 2 over p. And that's my condition for q1, q4. And this is a line passing through the origin. All right. Now let's come to the interesting case, which is the new counterexample that I was talking about for Q3, Q4. And unfortunately, in this setting, you see a blank page. I can't really draw it because it only makes itself felt for n greater than equal to 2, which means that the actual dimension of the Heisenberg group greater than equal to, at least for n equal to 2, the dimension is 5 or more. So I can't really draw a picture here, but let me just try describing how it is. In fact, for n equals 1, I think it reverts. You just recover the ball example or something for this example. So, right. So as I said, this replaces the nap example in the Euclidean case. So let's first try to see how one might consider to build a nap example for the Heisenberg case, and then what are the changes one needs to make to get this example. So let me consider Q delta. So my test function will be the characteristic function of this set, Q delta. And what is Q delta? All right. So remember, we have now 5 components, y1, y2, y3, y4, y5. Right. What happens in the NAP example usually is that you choose certain directions to vary in a set of radius delta to the power 1/2, and the other directions to vary in a set, and basically one direction, the last direction to which corresponds to the codimension to vary in a set of radius delta. In our case, we have 2 codimensions, so maybe we'll choose 2 of the directions to vary in a set of radius delta, and the 3 remaining in a radius delta to the power 1/2. So maybe something like this: y1, y2, y3 is less than equal to delta to the power 1/2, and then so these correspond to the dimension of the sphere, and then the other, which correspond to the codimension, y4, y5 is less than equal to delta. So maybe this is the way one might think of generalizing the NAP example, although it's not also clear what it means for a NAP example in codimension 2. However, and I mean, you can go on like this, but the condition gives you, as I've said before, is not the optimal one. So you have to make some changes here. And what's the change? The change is that here for the delta 1/2 condition, one of these directions will not be vary in a delta over 1/2 radius, but delta radius. So one direction has to be moved here. And which is that direction? That direction is also a specific one. It's not like any direction, it's the y2 direction. So what I'm saying is you have to change this condition to be something like this. So only y1 and y3 are less than equal to delta to the power 1/2, but y2, y4, or let me write it like this: y2, y4 less than equal to delta, and y5, let me just write it separately, is less than equal to delta. This is the right condition. Okay, so why y2? Why does y2 go with y4, right? That the reason seems to be because of the way this product, the Heisenberg twist, works. So in this case, if you look at the J matrix, which comes into picture in the last coordinate, it's a 4x4 matrix, and it looks like this: 1 0 0 1, negative 1 0 0, negative 1 0 0 0 0. And you see that the fourth component always interacts with the second component. Oh, sorry. This is one, right, identity. So the fourth component always interacts with the second component, and that somehow comes into play when you are building up these examples. It seems like the best possible example you get is when you do account for that and these directions go together. That seems to work out. So this is what we'd be going to do. What we'd be going to do also for building up the the set of test points. So so our test function is the characteristic function of Q delta. So let's call it F delta. And then what's the LP norm of this? So I've written these things down for n equals 2 or d equals 5, but you can just straightforwardly generalize it to any n. Basically, what will happen is instead of these two directions, you would take the remaining 2n minus 2 directions here. And here you'll have 2 directions, and here you'll have 1 direction. So the volume of the set would be, you'll have 2n minus 2 directions for delta to the power 1/2. And then you have 3 directions for delta, then 1 over p. So this would just be delta to the power n plus 2 over p. Again, there's a lag. Right. So this is Q delta. Right. And then what are my test points gonna be? So my test points are gonna lie in this set. And again, you use the same philosophy that x2, x4 go together. So it's x1, x2, x3, x4, x5, such that x1, x3 is less than or equal to delta. Then these would be together x2, x4 minus t. So this is the NAP type example. Of course, in the Euclidean NAP example, you would have just had x4 minus t is less than delta. But now you have x2, x4 the norm of that minus t is less than delta. Basically, they together are forming an annulus of thickness delta of radius t. And then finally, x5 is less than or equal to delta. Okay. And this is for 1t. And again, your total set would be union of these t, the delta separated. So you have R delta t. And what would be the volume of R delta? So this would just be, again, you have 2n minus, I'm sorry, I made a mistake. This is delta to the power 1/2, that's the point. Delta to the power 1/2 in the remaining directions, but this would just be delta. Okay, so that's the NAP example, sorry about that. So this would just be delta to the power 1/2 in 2n minus 2 directions. And then you have this only contributes 1 delta, and then this contributes another delta. But that is just the volume of one annulus, and then you're taking delta inverse number of annuli. So you have a delta inverse. So this would just be delta to the power n. And then you'll be looking at the LQ norm. So this is just delta to the power n over q. Yeah. And then finally, when you look at how big would your, how much of a portion this Q delta would catch when you take take averages centered at points in R delta t, you would see that MF delta x is greater than or equal to, and again the same thing will happen. It will catch a NAP type cap, which is of delta to the power 1/2 radii in 2n minus 2 directions, but delta in this one direction. So it's delta to the power 2n minus 2 over 2 times delta. So this is equal to delta to the power n again. And then when you build up again the same inequality, you would have something like delta to the power n over q times delta to the power n is less than or equal to delta to the power n plus 2 over p, which gives the condition n over q plus n is greater than or equal to n plus 2 over p. And that's the sharp condition for Q3, Q4. So this example is quite mysterious, and it works out well. And there are some algebraic reasons for why it works out, but yeah, there's something new and interesting. And I guess the takeaway is that those two directions need to go together, because that's why that's how the product works on the Heisenberg group. And there's something else about this example, which I'll maybe say at the end. All right, so after all these calculations, let's, so this basically shows how we arrive at the conjecture or the sharpness of our results. And now I would like to talk about the proof of the positive result. So, okay, now you have this conjecture. How do you actually go about proving it? And it turns out that at least for 3 of those points, Q1, Q2, and Q3, the L2 estimate seems to be the most important. It is the most important. Once you have that L2, the correct quote unquote L2 estimate, you will immediately get by interpolation all the points Q1, Q2, and Q3. So let's first focus on this L2 estimate. And in fact, we would be looking at space-time L2 estimates. So what do I mean by that? That when you take the L2 norm, you take L2 norm not just in the spatial variables X, but also in the time variable. So think of t also as a variable. After all, we are varying the t over the entire interval. Let's think of it as a variable. And that is why this is the notation I would use. So now just the difference is that I'm thinking of t as a variable now. So t is not in the embedded in the operator, but it's a variable. Okay. So then this operator A maps functions in L2x, so functions of 2n plus 1 variables, to those in L2 in variables x and t, functions of 2n plus 2 variables. This is how you should think of it. And again, the idea we use, which is what I was saying in the context of the Muller-Seeger paper before, is that we look at this operator A as a Fourier integral operator. And it's a bit technical, and I'll be not getting into all those technicalities, but the idea is that you rewrite it as an integral, as an with a complex exponential, but you will introduce 2 more extra variables when you do that. These we call the frequency variables. And why are you introducing 2 variables? Because my surface happens to be of codimension 2. So each of those frequency variables correspond to each one of the defining equations of the sphere of codimension 2. So and then using this, we can write the operator A as a Fourier integral operator. So this is introducing these frequency variables necessary to write it as an FIO first. And then we want a space-time L2 estimate for this Fourier integral operator A. For actual calculation, it's better to get rid of these frequency variables somehow once you write A as a Fourier integral operator. And if you have an L2 estimate, doing so is easy because you can use certain operations like a scaled Fourier transform or something, which basically is a way of getting rid of these frequency variables. And it's still nice because applying these scaled Fourier transform does not really change the geometry of the problem. So this is what we do. And then so we write A as a Fourier integral operator. From that, we get an oscillatory integral operator, just the usual way we think of it. And so that oscillatory integral operator comes with a phase function. Let's call it psi. And psi is a function of x, t, which are the variables outside, and y is the variable which is running inside the integral. So if you want, you can forget about all of this. Basically, this or maybe after the next slide. And this psi is actually the main the phase function that we want. Okay, so what's the underlying geometry over here? So let psi be the phase function associated with the oscillatory integral operator. And again, let me emphasize that x comma t are drawn from some suitable open set omega L. The L stands for left, which sits in R2n plus 1 times 1 comma 2, meaning it's a 2n plus 2 dimensional set. Whereas y is drawn from omega r for right, which sits in R2n plus 1. It's a 2n plus 1 dimensional set. And there's already some nice theory to understand the L2 estimates for this Fourier integral operator, which says that the L2 estimate on this operator is determined by its wavefront set. And how you should imagine it is like it's the direction of the worst decay, right? And that determines the L2 estimate. And this sits in the conormal bundle of the associated manifold, the manifold associated to this operator, which is a codimensional 2 manifold, which is given in this manner. So basically, if your codimension is actually defined by the space functions psi, then the conormal bundle is given this way. So at each point x comma t, the gradient of psi in x comma t would be in the conormal bundle, and similarly for y and gradient of y. If you look at the points y, this is the gradient of psi with respect to y. So this is important for these kind of problems, and because we use it to determine what is called rotational curvature. Again, there's some So the slide is not moving. Maybe I think it's stuck.
Yeah.
Maybe it moves in some. Yeah, sorry about that.
Maybe you can close it and then open it again or something.
Close. Should I join again?
No. Stop
No,
sharing.
you can stop sharing and then share it again.
Okay, now it's coming.
Yeah, open it again.
I think now it's coming. Yeah. Okay. I think it's a bit slow in. Let me see if it's. Yeah. Okay. Now it's doing something. Right. So yeah. This picture is important for the rotational curvature. So here I write another set which is very similar to the conormal bundle that I was talking about earlier, except there's a negative sign in front of the second gradient. And what in theory this is called in the FIO theory, this is called a canonical relation associated to the Fourier integral operator. And this negative sign is just for it makes some things work out nicely, but don't worry about that. So basically, in this theory, you often see a picture like this. So if you look at the associated canonical relation, which is given by this by the points and the gradient of the phase function, then you can define the two projections. So pi L, the left projection, and pi R, the right projection. So basically, pi L is just you project from the canonical transform. You just project x comma these left values. So x comma t comma gradient in x comma t of psi, and this will lie in the cotangent bundle of the set omega L, which is where x comma t lives. And similarly, you can think of the right projection, which is just you project these points. So it's y and negative gradient in y of psi. And this will lie in the cotangent bundle of omega r, which is where y sits. And Hörmander, it's a theory of Hörmander, it's a classical theory, which says that the best L2 estimates correspond to the situation when this C is locally the graph of a canonical map, which basically means that both the projections pi L and pi R should be local diffeomorphisms. So this is all the theory, but it means something very concrete in terms of the phase function. So this is the case when the determinant of the mixed Hessian. So the mixed Hessian is of the phase function. So what do I mean by that? So you take the phase function, first take its gradient with respect to the first set of variables, which is x and t, and then take the derivative of that with respect to the second variable, which is y. So that will give you a matrix. So the case of the best L2 estimates is when the mixed Hessian is bounded away. So the determinant of this matrix is bounded away from zero. And this is what is called the case of non-vanishing rotational curvature. Right. So, of course, I mean, in our case, we want the best L2 estimates. So our question was, does this happen for our case? And of course not. It fails, and it fails spectacularly for a very silly reason. X comma t is a 2n plus 2 dimensional vector. Y is a 2n plus 1 dimensional vector. This mixed Hessian matrix is not going to be a square matrix. It's going to be a 2n plus 2 cross 2n plus 1 matrix. So of course it will not be invertible. So you have an extra variable there, which is the time variable. So since in our setting, omega L has dimensions strictly greater than omega R, the above situation could never arise. But the reason we fail is because of a silly reason. So because you have an extra variable. So the most natural fix that one might have is let's freeze one of the variables, and it's always t usually you freeze, right? That seems to be the extra variable. So let's just freeze t. And we freeze t, and then we obtain a fixed time L2 estimate for each operator at for a fixed t. Right, so let's do that. And then when we want to integrate over t, we are simply integrating over the interval 1 to 2. So let's just integrate that trivially and do nothing. So that's the most natural choice. Unfortunately, it's too easy. It goes wrong again. And this time it goes wrong because of some deeper reasons, not for a silly reason. So we do not get the best L2 estimates here again. And that's because even for a fixed time t, if you draw that picture, that pi L pi R picture, even though now you're projecting two sets of the same dimension, pi L and pi R are still not diffeomorphisms, but they are associated to what is called fold singularities. And this was used by Seeger in their paper. And what do I mean by that? What I'm saying is that even though the mixed hessian of psi in this case is a square matrix, its determinant still vanishes on some points. In fact, if you look at the surface, which is defined, if you look at the equation, which is basically the determinant of the mixed hessian is 0, then it describes a surface which is called the fold surface. And this is where things go bad. In fact, the nearer you can do a decomposition with respect to distance from the fold surface, and the nearer you go to the fold surface, the worse your L2 estimates get. So that's the problem. All right. So then what to do next? So then there's another fix. We know that the fixed time estimates go very, very bad when you go near the fold surface. But you have now an extra variable t. You don't need to be in the fixed time regime. So why not use that time variable? So what we do is we have a choice. We have 2n plus 2 variables. Let's choose which variables we want to look at the rotation or the mixed hessian in. So choose which variables to freeze. And with that, and this choice will depend on how far or near you are from the fold surface. Because again, the fixed time estimates go bad near the fold surface. So you have to make a decomposition like that. So away from the fold, the fixed time estimates are good. So away from the fold, let's freeze the variable t. But what to do near the fold? So in our paper, we show that near the fold, there exists another direction. Let's call it E kappa. And this is in R2n minus 1. So it's not the time variable. It's also not the last two directions. It's some direction different from that. But there exists some direction which is not the time direction, such that if you look at your variable x tilde, which is you take x1, x2, dot, 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 but you just omit the x kappa. So and then you take the time variable, right? So this is x tilde. And then you look at the mixed hessian of psi with respect to x tilde, t, and then y. That determinant will not vanish on the fold surface. So you can't so you are using the time as a variable. You just freeze some other variable x kappa on the fold surface, and that would again give you nice L2 estimates. So this is the idea. So basically, this is what's happening. You have two regimes: away from the fold surface and then near the fold surface. Away from the fold surface, you freeze t and obtain optimal L2 estimates for 8t for each fixed t. But near the fold surface, you freeze x kappa, and then you obtain L2 estimates for a with each frozen x kappa. And then in the end, you will integrate in t, but here you will integrate in the x kappa, and a priori by some partition of unity, you can assume that x kappa lies in some compact set. So this is the idea. And when you use this idea, you actually get the exact L2 estimate that makes things work. So I keep talking about that. Let me just also say quickly what those are. So the geometry remains the same, but what you have to do is you need to split your operator up into pieces. These are Littlewood-Paley pieces. So this is composition with the Littlewood-Paley projection operator mapping to an annulus of size 2 to the power k. Right, so you decompose your operator in this way, and then we look at L2 estimate for each operator ak. And if you use this idea, you get the best possible thing over here. So this is the decay you get. This 2 to the power k is going to be there. This is some technical reasons, and this, I mean, our points already account for that. But this is the main thing that you get. So you get a decay, and you get a decay in all the you gain in all the directions, all the 2n plus 1 directions. So that's why you have such a nice gain over here. And this comes from Hörmander's L2 estimates. And suppose we had not used this thing of of using different variables away and near the fold, and had just gone with fixed time estimates throughout, meaning things would have gone worse at the fold. And how worse would they have gotten? This is how worse they would have gotten. We would have lost 1/6 derivatives, and this is a major loss. And this always happens for operators with fold singularities. And these kind of space-time L2 estimates in this context have been used before by Narayan and Thangavelu in their paper, and also Junil Kim more recently. So this is not new, but it works out well. Right. So now we have the nice L2 estimates, and what's the idea? So you gain a lot here, 2 to the power k. So this is the L2 estimate. 2 to the power k, 2 to the power negative k, 2n plus 1 over 2. And then you have some nice, almost trivial estimates available at some of the endpoints. So this is the L1 to L1 estimate for the AK. So everything is happening for the operator AK. And this is something like you don't really gain or lose anything. It's just like uniformly bounded, but it's bounded for each piece AK, so you can't really sum it up. It's very bad for that. And also for L infinity to L infinity, it's bounded by a constant. So you gain nothing here and here, but you gain a lot in this middle. So then you do interpolation and you see how far you can stretch things, and it turns out between Q1 and this point L 1/2 point, when you stretch it out by interpolation, you can actually cover the entire ground. However, on the other side, you can only go as far as Q2, but you can go up till Q2, so that gives you the positive result. And similarly for Q3, you use an L1 to L infinity estimate. You interpolate with an L1 to L infinity estimate, where you also lose. Here you actually lose 2 to the power 2k, but again you gain a lot over here. So then you can stretch again and you reach till Q3. So that already gives you 3 points, Q1, Q2, Q3. All that is left now is Q4. Right? And I feel like I'm already out of time. So let me just very quickly say what happens here. So the idea over here is to use a Stein-Thomas type argument. So, and not directly for Q4, but as it turns out, you can get Q4 by interpolating between an L1 to L infinity estimate and another space-time estimate, which is from L2 to another point, LQ5. So you reduce the estimate to Q4 to an L2 to LQ5 estimate, where Q5 resembles the Stein-Thomas exponent a lot. Right? And you used, in fact, the Stein-Thomas argument over here. So there, what happens is you, instead of looking at an L2 to LQ5 estimate, you try to prove an LQ5 prime to LQ5 estimate for the operator transpose composed with the operator. Okay. And this estimate now brings us to the anti-diagonal. So then what we want to do is we want to get this estimate by another interpolation between an L2 to L2 estimate for the operator composed with its transpose and an L1 to L infinity estimate. The L2 L2 estimate is the one you have already gotten. You can just use that. The L1 to L infinity estimate is the main part. And for the L1 to L infinity estimate, you again have some theory. You have the Carleson, Sjölin, Hörmander curvature condition, which relates. And again, you have to look at the geometry of the phase function. So this theory basically says that the decay you get for the L1 L infinity estimate, the gain you get depends on the number of non-vanishing principal curvature of this surface sigma x comma t, which is parameterized by the gradient of the phase function in the variables x and t. And this surface turns out to, for fixed x and t. This surface, it turns out, is a 2n plus 1 dimensional conic surface, meaning the maximum possible number of curvatures it can have in any case is 2n. Right, one curvature will always vanish. And again, in our paper, we showed that in fact sigma xt has exactly 2n non-vanishing principal curvatures. So this was again something which was surprising to us, because sigma xt is related to this phase function psi, which was related to a singular surface, a codimension 2 surface. So it was a surprise that even then the curvatures do not vanish, and you get the maximum number of curvatures that you can get. So once you prove that, you get a very nice L1 to L infinity estimate. You get a gain, you gain 2n over here, and this 2n is the same, comes from the 2n non-vanishing principal curvatures. So that's how, that's why it's important to have those. So this is the basic idea. I think it's stuck again. Okay. So and then maybe in the last slide, let me just talk about extension and something which remains open. So in fact, our positive result extends to Metivier groups, which are of Euclidean dimensions. So this is R2n times Rm. So instead of the one perpendicular direction, you have m, the center is of dimension m basically, and that means the averages over spheres, the spheres we are taking are even more singular. They have codimension m plus 1. So, however, you should still think of m as small compared to n. So the situation is still closer to taking averages over spheres, sorry, over surfaces rather than averages over curves. So m is small, but it's still more singular. So our positive result generalizes to the setting as well. It's a bit technical, but the same idea. But we could not prove sharpness here. And all the other counterexamples are generalized except the new one, the Q3, Q4 one we were not able to generalize it to the setting. So, and because of that, we do not know whether our result is sharp for Metivier groups. Can our counterexample be generalized, or does there exist a new one in the setting? We don't know that. But so that's where I'd like to end. Thank you for your attention.
Yeah, thank you very much for a very interesting talk.
Thank you.
So let's see if there are some questions or comments.
Yeah, maybe just a somewhat silly question. So the method seems to be general. So does it work for other hypersurfaces in CN? Not
Other
just the sphere?
Right, that's a good question. Right. So I mean, the sphere, even though here it's of codimension 2, the nice thing it has is like the actual curvature. It has a lot of curvature. And if you are looking at other surfaces, especially the ones specific to the Heisenberg group, there might be some other problems there. Maybe not fold singularities or something, but just the geometry, maybe don't have curvature. There might be some flat points or something, and that would lead to additional difficulties.
Okay. Yeah, thank you.
Thanks for the question.
So what about the spherical means on the Korani sphere? You have some results.
Yeah, right. So you and Pritam have this result for the lacunary means, and right. So this is something I'm looking at right now, and this is there's problems there. Like this is what I was saying. So if you draw the Korani sphere, so that's Korani sphere is basically of codimension 1, so that's good, right? But if you draw it, it's like this. So these points are kind of flatter, and that is a problem because as it turns out, the rotational curvature is all good, and this is something which is known. But this other curvature that I talked about at the end goes bad really badly, and so you need to do some other things. But I'm working on that, and seems there are some results here. Thank you for the question.
Are there some more questions? Yeah, if not, let's thank Rajula for a very interesting talk once again.
Thank you.
Thank you.